Development of an efficient design for a lunar survey vehicle began in this laboratory soil bin with tests of an articulated wheeled scale model. Here the vehicle model is shown being put through performance tests in a bin containing a loose pumice material arranged with undulations and irregularities to simulate a likely lunar surface condition. This model consists of 6 large light wheels, all motor-driven, coupled by elastic rods, which enable each of the 3 units to dip and roll with respect to one another. It carries a trailing electric cord for its laboratory power supply. Because of uncertainty regarding the composition of the lunar terrain, tests were also performed under conditions that included extremely rough terrain characterized by large obstacles. This small-scale wheeled vehicle appeared to offer many promising advantages. A high degree of overall mobility and simple and reliable operation. Since this wheeled model showed satisfactory ability to climb obstacles, bridge them, and in general deliver sufficient traction to maintain forward movement under the most trying conditions, it was selected for further development. A dramatic demonstration of its climbing ability is given in this experiment, where it successfully crossed an obstacle 4 times its wheel radius. A large-scale lunar weight vehicle was then built, and a laboratory test run over a step obstacle 5 feet high. It, too, demonstrated the obstacle crossing ability of the model vehicle, derived in great measure from the extreme flexibility of the frame. This test-bed vehicle is 12 feet long, 5 feet wide, and weighs only 66 pounds. Its light weight permitted an evaluation of its performance under lunar gravity conditions. Field test terrains were selected to simulate possible lunar surface conditions. One strong likelihood is a terrain represented by this loose wind-blown sand. When disturbed, this sand flows in an almost fluid manner until it assumes a natural slope, known as the angle of repose. Maneuverability tests were run on the dunes to study the vehicle's slope climbing capability, steering performance, and ability to negotiate obstacles. Here, a steering test on the top of the dune is shown. The steering commands are given by radio remote control with a time delay of 3 seconds, which corresponds to the transmission time required for signals from Earth to Moon and back. Dacron fabric, which covers the wheels, is tough but flexible, so that the spring wires protrude slightly, like tire lugs, to hold the terrain. The vehicle is shown here on a slope of approximately 33 degrees. Actually, it ought to be impossible to climb this slope, since any force applied to this loose sand should start it flowing rearward. However, the high slip of these wheels removes enough of the soil material to momentarily reduce the slope, permitting forward motion. The extreme temperatures and bombarding meteorites of the lunar environment make pneumatic tires undesirable, so flexible spring wire wheels are used. With low wheel loading, this results in a ground pressure of about 1/10 of a pound per square inch, making for excellent soft ground crossing ability. Another suggested terrain condition on the Moon is a rugged rocky surface, such as that encountered in a crater of volcanic origin. The material on the surface is loose and easily dislodged, and the soil consists of a jumbled mass of pumice blocks that range in size from a truck to a baseball. This field obstacle test was planned to consist of one long maneuver to be accomplished from slope to slope of this volcanic crater. The aerial distance from rim to rim is about 500 yards. The soft wheels tend to envelop small obstacles, reducing the shock transmitted to the vehicle frame and reducing the energy required to surmount them. The test bed vehicle weighs 66 Earth pounds. Under low lunar gravity, 330 pounds of payload could be added with similar vehicle performance. Natural obstacles often showed up which tended to imitate those provided in the laboratory. They helped demonstrate again the vehicle's ability to cross chasms and to successfully climb the large natural obstacles of rugged terrain. If the lunar surface were indeed to be either very soft or very rugged, it was decided that a lunar survey vehicle based on this concept would be suitable. A pre-prototype vehicle was then built based upon information from the previous test programs and designed to integrate with the Surveyor spacecraft. This vehicle weighs about 40 pounds, is 4 feet long with 12-inch wheels. The wheels and all the high-speed frictional motions are hermetically sealed. The wheel drive mechanism shown here consists of a motor followed by a gear reduction, which transmits motion to the wheels through a wobbling bellows. The only elements exposed to the lunar environment are the very low-speed wheel bearings. Each vehicle is planned to carry a hermetically sealed soil mechanics instrument, here shown under test. This instrument will measure the bearing strength of the lunar surface, which can be correlated with similar Surveyor measurements. It operates on the principle of force amplification by acceleration and deceleration of a mass at different rates. As shown here, the instrument then transmits the force, acceleration, and penetration of a plate touching the soil to an oscilloscope. For actual field trials, a 10-foot tall rod with 5-foot crossarms is used as a surveyor's stadia rod. This rod, mounted on the vehicle, is inflated shortly after deployment of the vehicle from the spacecraft. It is observed by a TV monitor, which here simulates the television camera mounted upon the Surveyor spacecraft. This TV camera would be remotely controlled from a station on Earth. Its screen is marked with crosshairs to position the relative motions of the stadia rod as it moves across the picture. So, here the entire test facility is pictured during a demonstration run. The survey vehicle proceeds in short steps across a specially built test area called a lunarium, which is intended to simulate the lunar surface. Its movements are followed by the closed-circuit television setup. During the stop and start progress of the vehicle, turn and maneuver commands are given only during the stop intervals. Back on Earth, a monitor console would permit observation of the vehicle's progress. The operator would actually receive pictures only while the vehicle is stationary. By making suitable observations of the stadia rod, he would be able to determine not only the vehicle's distance from the spacecraft, but its elevation and attitude. Another advantage of the start and stop mode of operation is that it permits the operator to give steering commands in time to avoid potentially destructive obstacles. The vehicle normally proceeds for 3 seconds, then stops, receives a steering command, and proceeds again. 3 seconds also provides decision time for the operator. The prototype vehicle's progress is here shown across a flat portion of the lunarium. The facility includes a large number of boulders distributed in random obstacle arrangements to form maze problems in navigation, and a number of crater-like bunkers of substantial slope. This 30-degree slope is built of a common sand. It is to be noted that the stop intervals can be as long or short as the operator desires. Here, practically instantaneous go commands result in virtually continuous vehicle motion. The pre-prototype model is shown demonstrating performance at its earth weight of 40 pounds, so that a deliberately stiff wheel construction has been used, and a stadia rod of almost twice the lunar weight has also been used in order to provide resistance against wind loads on Earth. The alternate stripes on the stadia rod form coded length and recognition markings for TV picture study on Earth. Climbing tests were run over obstacles which were both equal to the wheel radius and greater than the wheel radius. Despite the special difficulties of Earth gravity, stiffened wheels, and the heavy stadia rod, the vehicle crossed obstacles several times its wheel radius and gave substantial promise of successfully accomplishing the objectives of a Surveyor Lander survey vehicle. With the release of a Surveyor program decision to use a long-range, versatile lunar roving vehicle on the 2,100-pound Surveyor spacecraft, an analysis was made of the payload volume, here represented by a white box, to find the largest vehicle which it could reasonably accommodate. The vehicle would fit the volume and center of gravity requirements if its spring wheels were deformed, as in the stowed flight condition. During deployment from the spacecraft, a mechanism shifts the vehicle to a ready position upon a signal from the Surveyor Control Data Console, and the flexible frame is released. This vehicle model is made lunar weight so that representative wheel and frame spring constants can be used for stowage tests. The model is 6 feet long, 3 feet wide, with 18-inch wheels. No stadia rod or batteries have been added in order to approximate lunar weight. Electric power is supplied through a trailing cord. In one possible lunar situation, TV cameras would be mounted upon both Surveyor and vehicle. The following sequence demonstrates the previous maneuvers as they might appear on the Earth monitors from the 2 TV cameras. Here, the vehicle is seen from the spacecraft as it is just deployed, and then in the course of its progress toward a slope. From the vehicle camera, the slope appears like this. Again, from Surveyor. From the vehicle TV, we see the top of a slope approaching. And then the Surveyor camera catches the vehicle at the very crest. And so the progress appears on the television monitors. This series of tests indicate that the vehicle concept is compatible with Surveyor stowage and CG requirements, uses a feasible deployment mechanism, and also demonstrates a high degree of mobility over various types of terrain. In addition to these tests, more detailed studies are being pursued, leading to a Surveyor lunar roving vehicle design. Representative of these studies is an investigation of thermal problems. A series of full-size thermal models were built for a detailed study of radiation view factors. The technicians are preparing the model for the JPL photographic technique, which is used in one step of the investigations to check for adequate nighttime heating and daytime cooling under lunar conditions. A telephoto lens photographs the reflection of the vehicle and its surrounding volume, which appears in a small, convex parabolic mirror. This study represents only one portion of a many-faceted research and development program directed toward an advanced, space-qualified lunar roving vehicle for Surveyor.